Namaste students, welcome back to Rama Teaches You. Today we are going to do the IB Physics section E, Radioactive Decay. That is the E3 section. This is the last section of the book and this is the third part of the last chapter, E3. Okay, and radioactive decay is, I think you must have learned you must have had some information, like you must have heard about uranium and all the other, like plutonium, thorium, all these elements before in various chemistry classes. So this is going to be a culmination of all the other topics that we have learned so far. Okay, now let's actually go through it. Yeah, one second. Let's start. A, C. Okay, full screen. Radioactive decay. E3. Are some isotopes more stable than the others? Okay, what is the reason for stability of some isotopes whereas other isotopes are not stable? Simple example. Hydrogen has three isotopes: protium, deuterium, and tritium. Protium and deuterium are stable in nature, whereas tritium is a radioactive element. Okay, a proton and two neutrons gives you a tritium. Usually hydrogen has only one proton, right? But one proton, one neutron gives you deuterium, and one proton and two neutrons gives you tritium. So tritium is radioactive. But the rest of the two other isotopes are pretty much stable. Similarly, carbon 12 and carbon 13 are stable in nature. But carbon 14 is radioactive. And carbon 14 is actually used for calculating the age of various stones, organic matter. Okay, the basically, what do you say, the the time, the earth's lifespan. Okay, sometimes, okay, most organic matter that you see, okay, is used. Carbon 14 is used for dating the age of the dinosaurs. That dinosaurs existed 70 to 80 million years ago. The dinosaurs existed. So basically, all of this thing is done by carbon. But carbon 12 and carbon 13 are not radioactive. Only carbon 14 is radioactive in nature. Okay. Uranium 238 is actually pretty stable. But uranium 235 is radioactive in nature. It's an isotope of uranium. Why is that so unstable in nature? One second. So, in what ways can a nucleus undergo a change? What are the various ways in which a nucleus undergoes a change? How do large, unstable nuclei become more stable? How can random nature of radioactive decay allow for the predictions to be made? Okay, so sometimes radioactive decays have certain um, very unique properties. One of the interesting properties is that almost every element heavier than uranium in some point of time, almost every element heavier than lead, after a certain lifespan of after like thousands, millions, or even sometimes very small time like micro milliseconds, it turns into lead. Okay, lead is stable. Yeah. Right? Huh? Yeah. Is this the half life? Yeah, basically, yeah. No, but what I'm trying to say is, in nature you have radioactive elements because they have certain properties in their nuclei or in their structure of atom that makes them unstable. Okay. Yeah. Now, and they usually nature sometimes slow, sometimes fast, always wants to move towards stability. Okay. When you throw up, I have always explained this to you. When you throw a piece of rock upwards, it will always come down and fall because the potential energy is zero. It is more stable in the ground rather than in the air. That's why it comes down. Okay, so something like that also happens in in atoms also. It's an atomic property. It's a nuclear property, to be more precise. Now, the story of discovery of radioactivity is well known. On March 1st, 1896, Henry Becquerel developed one of his photographic plates. He saw on the developed plate the outline of some uranium salts that had been lying on top of the wrapped photographic package. So he observed that some amount of uranium that was, see, basically you had a plate here. On top of the plate you had a sheet, and on top of that sheet you had uranium on top. But uranium had somehow seeped through the piece of paper onto the photographic plate. Realizing that something about uranium materials caused the effect, he looked further and confirmed that the radiation from uranium was the cause. So basically, this radiation was able to pass through a solid paper, okay, and affect the photographic plate inside. Okay. Becquerel was inadvertently repeating the same discovery made by Abel Nipice de Saint Victor 40 years earlier. Now, Nice, 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 however, did not pursue the idea. Some thought he reported it to the French Academy of Sciences at that time. Okay, like it's always the case, right? Like many people have the same idea, but only the right person at the right time gets the credit. Okay, now the uranium material near Becquerel's plate was decaying to form a more stable substance. What drives these changes to stability? This is matter of internal balance within the nucleus, and it is driven by the interaction that occurs between particles in nuclei of all atoms except hydrogen, the simplest of all atoms. Because hydrogen cannot decay because it only has one, right? It only has one proton. If it decays, it will decay into nothingness basically. Okay, as you may expect from work in earlier themes, the changes are driven by energy consideration. Everything is related to energy, every single thing, right? Everything is related to energy. When the nucleus can move to a state where the amount of internal binding is greater, then it will do so. Okay, see, basically what happens, the nucleus is made up of protons and neutrons, right? Now, I have already told you this, that there is a repulsion that exists between two protons. Okay. Now, ideally speaking, if there existed only the electrostatic force, then atoms would never coalesce because the nucleus would never be able to come near each other. There is another kind of force called the strong force, which is holding the nuclear force, which is holding these particles of protons and neutrons together. Okay, the nuclear force does not care whether you are a proton or a charged particle or a neutron or a neutral particle. It will basically put the same force between two protons, two neutrons, and a proton and a neutron. Always. This is called the nuclear structure. This is what you need to understand. In Indian syllabus, we have this chapter in class 12th called the nuclei, where they tell us that some amount of binding energy is required to hold all these nuclear materials together, the protons as well as the neutrons. Okay, sometimes the binding energy is greater than the repulsive energy, which makes the nucleus pretty stable. Sometimes they are equal to the repulsive energy, sometimes they are less than the repulsive energy. Okay, understood? It's like this, Trupat, Akshay. Think about this. Okay, now you are holding your hands like this. Okay, now someone is just putting footballs in your hand. Okay, he's putting one football. It is easy for you to carry that football. Two footballs, again easy. Three, again, like it's a bit difficult, it's a bit awkward, but still easy. Four, five, six, seven, eight. Okay, eight footballs, you are somehow trying to hold it together. Would you, a single person, be able to carry 10 or 12 or 15 footballs? No, right? Why? Because even if you try to balance it, if you try to move slightly, one of the footballs could actually fall from your hand and touch the ground. So you can only hold certain amounts of stuff in your hand. Similarly, a nucleus can only have a certain amount of nucleons in itself that allows it to stay stable. Okay, now the degree of internal stability is crucial to determine the outcome of the radioactive decay process. This topic describes the principal ways in which radioactive materials decay. You may already know these as alpha decay, beta decay, or gamma photon emission. Okay, so alpha and beta are particles that are coming out of the nucleus of an atom, whereas gamma is pure radiation. Okay, it is pure photon, it's pure radiation. That is why it is more dangerous. Okay, for every radioactive nucleus, the decay process is dictated by the cause of nuclear instability. Okay, for example, if you are more stable in nature, then your decay will be lesser. For example, if you are a healthy person, like you go for a run, okay, you eat healthy food, you always do yoga, you meditate, you always you have a perfect health. Everyone has to die. You will die a little bit later than a person who smokes, who drinks every day, who basically has a very bad lifestyle, who does not sleep enough, who does not eat his food in the right time, who always has stress. That kind of person would perish sooner, right? Ideally speaking, like at the end of the day, life is in the hands of God. But ideally speaking, we know science has proven that a healthy person may live longer and a unhealthy person may live shorter. So basically, the same logic can be applied to nucleus also. A healthy nucleus, a stable nucleus, would have a longer radioactive decay time. So that means it will decay into another elements, but it will take a longer time. But an unstable element would decay much sooner, right? It would decay much sooner. Clear? So some nuclei can have too many protons, others have too many neutrons. The radioactive decay process corrects these imbalances. As a nucleus undergoes a decay, it moves to an increasingly stable state. Look at the example that I told you about football. Okay, ideally speaking, you can carry six footballs in your hand with complete stability. Okay, but you being a little bit lazy, you try to carry 12 footballs with you. But when you are walking, the extra six footballs actually fell off. And when you reach the house, when you reach the room where you had to place them, you were carrying the ideal amount of six footballs. Okay, so basically, instability eventually leads to stability. That's the lesson I want you to take from this. Okay, now a decay chain is the basis of the way in which a large unstable nucleus move towards stability through decay. Through radioactive decay, an unstable nucleus moves towards to become a more stable nucleus. This happens not by a single one-off change, but by a series of incremental and simple shift in the balance of nucleons. Slowly and slowly, the unstable atom will throw out one each and every single nucleon, sometimes two nucleons, giving you a what, sometimes one nucleon. So basically, if it gives out four nucleons at once, you will have an alpha particle. Sound understood? Now, the radioactive decay is a random process. However, even random events can be managed using statistics. The larger the number of atoms in any manageable sample of a material means that the averages can be predicted and that the predictions are accurate to a higher degree. For example, let's talk about probability. Akshay, if I ask you to toss a coin three times or five times, okay, or six times, let's make it a round even number. Can you say with certainty that the heads will come three times and tails will come three times? But if I ask you to toss the coin 1 million times, then you could say that the probability of you receiving half, like half heads and half tails, will be much more closer, right? So basically, that's what they're trying to tell here. The larger the number of atoms in any manageable sample of a material means that the averages that are predicted will also be to a high degree of accuracy. Understood? Okay. Now, randomness means that the mathematics of radioactive change is well understood because it depends on the knowledge that radioactivity is proportional to the number of active nuclei present in the sample. Predictions can be made from this straightforward starting process. Let's start the topic. What are the stuff that we are going to learn today? Oh, this whole section is not there. No, just some background radiation. Oh, background radiation. Okay, fine. So, isotopes, nuclear binding energy and mass effect. Oh, mass effect is going to surprise you like hell. Okay, it is amazing. Now, you have learned that mass can neither be created nor be destroyed. Yeah. Yeah, it's wrong. The variation of binding energy per nucleon with nucleon number. Very good. Mass equivalence, mass energy equivalence, the existence of strong nuclear force. the random and spontaneous nature of radioactive decay. Again, a truly amazing topic. Alpha, beta, and gamma radioactive decay. Neutrinos and anti-neutrinos. This is something even I haven't learned. Like before this video, I have to become a master in this chapter. Okay, because that's not part of our physics. Okay, the penetrating and ionizing ability of alpha beta particles and gamma rays, again a topic that I haven't studied. Okay, no problem. Before I reach this topic, I'll become no. Yeah, I will make myself a master in this topic as soon as. Now, then, activity, count rate, and half-life for radioactive decay process, and their changes for integral value of half-life. See, the thing that I enjoy the most is when I teach people from outside of India, I get to have a chance of learning something new with themselves also. Like in maths, when I was teaching one of my students in US, the algebra. Okay, when I was teaching her algebra, I learned a couple of new things. When I was teaching another student calculus, I learned that there are a lot of calculus topics that are not being taught in India. Okay, so it's a good opportunity to learn something new. I want you to study and look at this exactly the way I do it. Okay, it's not something that's supposed to be a headache. It's something that is supposed to open your eyes. Like for the first time when I taught you thermodynamics, we will go through all the chapters again. Da. Okay, before your final exam, we'll go through all the chapters once again. Now, the background radiation. So, next, for introduction. Radioactivity is nuclear change. An unstable atomic nucleus will sooner or later decay into different elements with emissions of one or more nuclear particles. These particles transfer energy from the unstable nucleus through ionization and other process to another atoms with which they collide. These could be atoms in a living cell. Okay, for example, see, if I throw a ball at you, okay, if I throw a cricket ball at you, it will hurt you, right? Why will it hurt you? Because I gave the cricket ball some kinetic energy, and when that kinetic energy having cricket ball hit your body, it transferred that kinetic energy into a momentary impact or potential energy in your body, thus creating a damage. Similarly, what are they trying to say? See, an unstable atomic nucleus will sooner or later decay into different elements with the emission of one or more nuclear particles. If it's one nuclear particle, it will be some other element. If it's like multiple nuclear particles, it could be like an alpha particle. Okay, these decays transfer energy from the unstable nucleus. So basically, when you eject out a particle, what is happening? The unstable energy that was present inside the nucleus has gone and basically transferred itself into this ejecting particle, and this ejecting particle is taking that energy away. Okay, now these particles transfer energy from the unstable nucleus through ionization and other process to form other atoms with which they collide. Now these emitted particles are going to collide with the surrounding elements around them, right? They're talking about a chain reaction in uranium, where basically if one uranium atom breaks, it releases neutrons which create an impact on the neighboring uranium atom, thus releasing more neutrons, and those neutrons basically collide with four other uranium atoms, so thus chain reaction is created. That's what a chain reaction looks like. Okay, the damage from these collisions drives cellular changes and can lead to evolution of organisms, but it can also lead to cell mutations. Radioactive decay has been an essential process, but it also a potential damaging one. For example, when Bruce Banner was basically trying to protect his research partner or his girlfriend in that video movie, no, basically what happened? He basically placed himself between him and the gamma radiation, right? So basically he absorbed a lot of gamma radiation. Ideally speaking, if a person absorbs that much amount of gamma radiation, he only has hours to live. Okay, hours. Within hours he should die. Okay, so that's what they're trying to say. A lot of cellular mutation is good. Okay, cells usually evolve. Okay, who knows, some radioactive collision from outer space could have given us a mutation called intelligence, where we start learning and basically trying to incorporate whatever we have learned. That's what the human brain does the best, right? It takes the experience, and on top of that, it plays the experience again and again and again to make it perfect. Yeah. Okay, so basically, it could be like that, or it could be, as we all know, cancerous. Basically, that's what happens whenever a uranium bomb is dropped, and when the bomb explodes, it releases radiation all around, and in the impact zone, everyone who was present has severe radiation burns or cancer, or they usually die. Okay, basically, the worst thing is that immune system gets completely shut down. Therefore, even a small cold could kill them. Okay, now we need to balance view of its benefits and drawbacks. There are a lot of benefits and there are a lot of drawbacks to radiation. Okay, in the history of science, some discoveries have been serendipitous. Okay, serendipitous, that is, they were unintentional. Becquerel observed radiation from uranium compounds because he left them lying on a photographic plate. Imagine if he was like a nonchalant, he didn't care about what happened. Or imagine if he never looked at the photographic plate in the first place. Okay, now many other phenomena have been observed when scientists were not looking at them. For example, William Rockton had discovered X-rays largely by accident. The year before Becquerel's discovery, playing with the properties of new rays soon led to their ability to see through bones inside the human body. Serendipity had led to the discovery of drugs and antibiotics, the development of new chemicals, and the invention of many devices from microwaves to the post-it note. In these cases, the scientists were able to use what might have been a failed experiment and realize the potential in their observation. Okay, so that's what you have to do with life also. Okay, if there's a saying, no, if life gives you lemons, instead of throwing them away, you make lemonade. Okay, yeah. So even if you have a wrong experiment, that could lead to something that is much more advanced or eye opening. Okay, let's look at this. Yeah. Now, Henry Becquerel placed the photographic plate in a drawer with some uranium compounds wrapped in a black cloth. When he later looked at the plate, why did he keep it in a dark plate? Because a photographic plate is light sensitive. Do you remember in the olden days when you were small? Yeah, you're, yeah, like a red book and like no, no, like when the parents gave us camera, they used to say that don't open the case. If you open the case, all the photos will become black. So basically, that's the thing. And there used to be red room, basically a place where the photographer actually opens the frame and does some chemical reactions and all, and he creates that photo. Okay, so basically he kept the photographic plate in a dark cloth in a drawer, but still the photographic plate got impacted. And that's what surprised him. That is the difference between a person who has an intuitive mind and an ignorant mind. Okay, when he later looked at the plate, it appeared to have come into exposure to light. The shadow of the metal Maltese cross. Okay, the metal Maltese cross. Look at this cross that you can see here, right? There's a cross observed here. Okay, located between the plate and the uranium compound. It is also visible. Becquerel realized that uranium compound was producing this invisible radiation. So there was uranium here, there was a cross here, and there was a plate here. So basically, the cross was blocking some amount of radiation that was coming from uranium, and the area that was not blocked by this cross was shown here. Transmitting it of the uranium. Yeah, it was the uranium that was affecting it. Okay, now isotopes and isotones. Okay, the chemistry of an element is determined largely by the configuration of the electrons outside the nucleus. Their numbers are equal to the number of protons in a neutral atom. So always and always, all the chemical properties that we study, the reactivity, or their valency, or their number of electrons, the ionization energy, the enthalpy. Okay, all these properties of an atom are given to it by the electrons that are surrounding the nucleus. Okay, yeah. So an electron plays a major role in the chemical properties of an atom. The nuclei has identical number of protons, must therefore have similar chemical properties and are known as isotopes. Okay, isotopes are two or more atoms that have the same number of protons but different number of neutrons. It should have been different nucleus. Different nucleus means basically atomic mass. Okay, same atomic number but different atomic mass. Carbon has 15 known isotopes. The two stable form of isotopes of carbon are carbon 12, also known as C12. Okay, now our carbon 12, C is the chemical symbol of carbon, and carbon 13. Like I've told, carbon 12 and carbon 13 are basically stable. Carbon 14 has the longest lived unstable isotope of an element with a half life of about 5,700 years. Okay, so basically 1 kilogram of carbon 12 will become exactly half a kilogram in 5,700 years. That's what half life means. Okay, yeah. 1 kilogram. Now, after 5,700 years, only half a kilogram of carbon 12 will be left. Okay. Now, these three isotopes are written as carbon 612, carbon 613, and carbon 614. They have 6 protons in the nucleus. Carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. Each neutral isotope has 6 electrons, and all isotopes share the same chemical properties. The reason why all isotopes can be placed in one single box in the periodic table is because the periodic table is based on what? The modern periodic table is based on the water shell legs. No. The number of protons, exactly. Okay, what you said is also right, but the answer that I was looking for is the number of protons. Okay, the term isotope needs a little care. It is often misused. Do not use it as a general name for stable and unstable nuclei, because an element can have many number of isotopes that are stable in nature. Isotope should not be used as a term to define stability or instability. Okay, say hydrogen 1 isotope is incorrect unless you are speaking in context of deuterium. Okay, now basically hydrogen has three different types of isotopes. Mainly, that's what we study, right? Hydrogen, deuterium, and tritium. The proper term for a distinct type of nucleus with a characteristic number of protons and neutrons is a nuclide. Okay, it's not an isotope, it's a nuclide. Say it with me. The name nuclide. Yeah. Okay. The proper term for a distinct type of nucleus with a characteristic number of protons and neutrons is a nuclide. So basically, you can say that carbon 12, carbon 13, and carbon 14 are three different types of nuclides. Isotopes, you can say nuclides. Okay. Next. Occasionally, it is helpful. Yeah, tell me. Yeah, again, I'll tell you. See, what is the reason behind it? They are telling. See, the term isotope needs a little care. It is often misused. Do not use it as a general name for a stable or an unstable nucleus. Say a H11 isotope. H11 isotope is incorrect unless you are speaking in the context of deuterium as well. So basically, you cannot use an isotope willy-nilly. Okay, until unless you are trying to distinguish it between two different types of isotopes. Understood? So basically, if you're talking about carbon 12, you cannot say carbon 12 isotope. That would be highly incorrect. But it will be correct if you are trying to distinguish it between carbon 12, carbon 13, and carbon 14. Oh, understood? So this proper term for a distinct type of nucleus it's like this, Akshay. Like basically, if you're trying to describe the various types of animals that we have, okay, yeah, like cat, dog, rat, mouse, giraffe, yeah, buffalo, okay, that is fine. But when you're trying to describe an event like this, you should not say cat, dog, then you have a Dalmatian or an Alsatian, okay, or a German Shepherd, because that is more specific.
Yeah.
Okay, when you're talking about different types of dog breeds, then you can say a poodle, an Alsatian, a German Shepherd, a Dalmatian, then it's fine. But when you're trying to yeah, tell me.
Yeah. So a nucleate is something like if it's the same rational carbon like different carbons. If you're talking about that, then it's nucleate.
Yeah, the proper term for a distinct type of nucleus. It's a distinct type of nucleus with a characteristic number of protons and neutrons is a nuclide. Instead of using an isotope, you will use the term nuclide. One of Rotung's early X-ray images. Can you see the ring that is in his finger?
Yeah.
Right? So basically, he does not have long fingers. The thing is, our hand, basically, the fingers start from here itself. Okay, the fingers don't actually start from here. They are basically starting from here, this portion. Okay, the different fingers are having just that there is cartilage and muscle around it. That's it. Okay, so his finger, the ring in his finger, and this finger is exactly the same. Okay, next.
Yeah.
Occasionally, it is helpful to have a name for two nuclides that share the same share neutron number, but have different proton number. These are known as isotones. Okay, two different elements having the same number of neutrons but different number of protons. Okay, for example, let's see. You have carbon 14. Okay, carbon 14 has how many neutrons? 8 neutrons. Like it has 6 protons and 8 neutrons. Oxygen 16, 8. It how many neutrons does it have? 8. So this has 8 neutrons and 8 protons. So these two, carbon 14 and oxygen 16, they both have the same number of neutrons. That is 8 neutrons and 8 neutrons. But one has 6 protons and one has, sorry,
Yeah.
8 neutrons and 8 neutrons, but one has 6 protons and other has 8 protons. Okay, so these two are known as isotones, having the same same number of neutrons but different number of protons. They are called isotones. Okay, an example. Yeah.
Tone and for neutron.
Yes, isotope is for same number of protons, different number of neutrons, and isotone is same number of neutrons, different number of protons. Okay, what is an isobar?
Isobar is
Same atomic mass but different elements altogether. For example, argon has 40 as its atomic mass, calcium also has 40 as its atomic mass. But in one place, carbon is an inert gas, whereas calcium is a very reactive metal. Okay, let's move on. Now, an example of a set of isotones that have 20 neutrons is sulfur 36, chlorine 37, argon 38, potassium 39, and calcium 40. Can you complete the full notation for these isotones? The first is carbon 1636. Okay, carbon 1636. Chlorine will be how much? This is 1636. This is 1737. This is 1838. Potassium is number 19 and calcium is number 20. So all of them have how much? All of them have for basically 20 neutrons each. Right? 1636, 20 neutrons. 17 is the atomic number of chlorine. That is not going to change. Number of protons will not be different for chlorine. Okay. Argon is 18, potassium is 19, and calcium is 20. Okay, let's move on. The radioactive decay. The radioactive decay occurs naturally. The nucleus of an unstable atom changes into a different nuclear arrangement by emitting combination of particles. The original unstable atom is known as the parent nuclide. The element that results from the change is the daughter nuclide. The daughter nuclide may or may not be stable. If it is not, then it will undergo a decay again, eventually reaching stability after a long series of decay of a radioactive series or a decay chain. So basically, every single time the parent nuclei splits or parent nuclear decays, it thinks that it may become stable. Sometimes it becomes stable, but if it's not stable, then it will again decay once more, resulting in smaller and smaller and smaller nucleus. Eventually, it will reach its stability. Okay, so the chain of events that take place between the parent nucleus and the stable atom that that it is eventually going to reach is called the decay chain. It's called the decay chain. Understood? Now, radioactivity is random. We cannot predict which nucleus is in a sample of radioactive materials will decay next. Okay, so it is totally random. If you have 100 nucleus, you cannot say the third atom is going to undergo radioactive decay. No, you can't. You don't have a clue which atom is going to undergo the radioactive decay in a sample. Understood?
Yeah.
Now, spontaneous. We cannot influence the rate of decay by changing the physical conditions of the sample, such as temperature, pressure, etc. So, it is spontaneous. That is, it happens on its own when it wants to and which atom it wants to. You cannot have any control over it. But you can have a control over its output, though. Okay, so basically the decay is going to happen, but the result of that decay can be used to create a lot of new stuff. Like basically a power plant where the decay which results in a release of energy could be used to heat water, which would eventually become steam and turn a turbine. That's how a nuclear power plant works. Okay, there is radiation happening. Okay, radiation happens. That radiation results in the formation of energy. Energy is used to heat up water. The boiled water soon turns into superheated vapor. That vapor at high pressure now turns a turbine. When a turbine is turned, eventually what happens? It's like a dynamo. Okay, generator. When the generator
Yeah.
turbine changes, it produces electricity, and that's how we convert radioactive energy or a chemical energy into electricity in a power plant. Okay, we could have influence over the various different types of events that are a result of the output of radiation, but you cannot control the radiation. Okay, it is a totally random process and it is spontaneous in nature. Okay, next,
Yeah.
nuclear changes during radioactive decay. The principal type of decay possible are the alpha decay. A helium nucleus is emitted by decaying nuclei. Okay, then a beta decay. An electron or its antiparticle is emitted or captured by a nucleus. Okay, it's called the beta decay. An electron
Yeah.
or its antiparticle or a positron. Okay, next you have gamma rays, gamma emission. The electromagnetic radiation of high energy, a gamma photon is emitted by the nucleus as it transfers energy when moving towards a lower energy state. Okay, when it
Yeah.
basically it's the release of excess energy that is taking place. This excess energy can either go through the gamma radiation, the gamma decay, or any other process as mentioned above. Okay, now let's slowly and meticulously try to understand what are the various types of decays that are possible. But before that, let's actually look at Mary Curie, the person who is like the she's like the godfather of radioactivity. Okay, Henry Becquerel, Mary Curie, and all these people basically sacrificed their life, okay, in the pursuit of radioactivity, because we all know radiation is a bad thing. Okay, now if you are exposed to excess radiation, you could have cancer. Mary Curie and her husband Pierre, both of them died due to radiation poisoning only. Okay.
Yeah.
Now, Marie Curie is sometimes described as the most famous female scientist ever. Her work on radioactivity led her to the discovery of two new substances, element radium and polonium. She shared the 1903 Nobel Prize for Physics with her husband Pierre Curie and Henry Becquerel. Okay, three people can at once share the Nobel Prize. That is something that I learned from Big Bang Theory. There's a TV show called Big Bang Theory, right? From there I learned that three people can have one Nobel Prize. Okay, the prize can be shared among three people. So these three people, Henry Becquerel, Mary Curie, and her husband Pierre Curie, all of them got the Nobel Prize in radioactivity in physics. She was later awarded the 1911 Nobel Prize for chemistry, and because not only she and became not only the first woman to win a Nobel Prize, but the first person to win two Nobel Prizes. She became the first person ever to get two Nobel Prizes. Okay, and that's a huge thing because during her time it was very difficult for girls, okay, especially women, to go into the field of science. They had a lot of stereotype on top of them. So not only she had to work, but she had to prove herself to these ignoramus people, okay, about her talents. So she deserved the two Nobel Prize. She remained the only person to have won a Nobel Prize in two different sciences. During the First World War, she endeavored the use of her scientific discovery for good. She established mobile X-ray units and acted as a driver to assist wounded soldiers. When she got to know about the X-rays that were coming out of her experiment, she used that X-ray to basically help the soldiers who were wounded in the battle. Okay, basically she because people for the first time could see the broken bones before cutting it, right?
Yeah.
She also realized that the use of radioactive sources for sterilizing wounds. While her scientific achievements brought her increased fame, she rarely accepted awards and donated prize money to the scientific institution. Einstein is reputed to have said that she was probably the only person not corrupted by the fame she gained. She was the world's famous woman and she had zero ego, and that is something that is very difficult to have. Okay, if to have that, see, basically why are they teaching you about her? Okay, what physics information did you get from her? You get to know that even if you become the king in your field, you have to remain humble. Okay, otherwise the fall would be very, very drastic. Okay, you have to remain humble even if you are at the pinnacle of your studies. Even if you are she was radioactivity that is, I cannot explain to you what contributions and what achievements of hers we are using it today. Okay, a lot of stuff. You must have had a fall, you must have done x-rays. Imagine, she is the one who actually introduced you to the concept of x-rays. Okay, so basically every time you go to a hospital and they do an x-ray for you, it's because of her. Okay, sorry for the deviation from the path. Let's come back. An unstable alpha particle emitter emits a particle that consists of two protons and two neutrons bound together. This particle is identical to the nucleus of a helium-4 atom. The overall change from the parent to the daughter is represented by a nuclear equation. So this is the parent atom. Okay, when a uranium atom breaks, what does it become? It becomes thorium. Okay, thorium plus 4, what is 4? Helium.
Four.
You get a helium. Okay, that 4, that's what I'm trying to say. See, basically you had an atomic mass of 232 for uranium, but if you subtract 4 from it, you get 228. And that 4
Yes.
different neutrons and protons, two neutrons and two protons that were removed, they became the alpha particle. Okay, similarly for polonium. Okay, Po is polonium. When it loses 4 nucleons, that is two protons and two neutrons, again you get an alpha particle. Pb is, you know what? What is Pb? Lead.
Yes.
Lead. Okay, so notice that one of these equations that emitted the alpha particle is shown as a helium nucleus, in the other with the symbol alpha. Both are correct. So you can either use He or you can use the term alpha to represent an alpha particle. Okay, the equation is balanced. Why? Because Whatever mass was present in uranium, the same amount of mass is present in thorium and the alpha particle. So the equation remains balanced. The left hand and the right hand side total for both A and Z are the same. The atomic number, that is the number of protons as well as the number of neutrons, are the same in both the two sides. Okay, you have 92 protons on the left hand side and at the same time 92 protons on the right hand side. Similarly, in for the both case downward also, 84 on the left and 84 on the right. Energy is also released during the decay. This is not usually shown in the equation. In alpha decay, energy is transferred to kinetic energy of both the daughter nucleus and the alpha particle. This has consequences for the motion of the products. Okay, so it's not just imagine this. Okay, you had an egg in your hand. Okay, an egg, and basically a raw egg in your hand, and it fell from your hand into the ground. Imagine when it fell. Okay, and it basically, when it falls to the ground, the shell goes like this, right? It goes in three different places, right? How much ever it breaks, does the egg remain there? No, right? It rarely does. Okay, another example, the best example that I can give you is that of these containers. Okay, these metal containers, when they fall, the lid usually goes very far off, right? It's annoying that how far it can go. It basically split itself, but when it split itself, it did not just stay there. It flew through like 3 or 4 meters away. Okay, similarly, when a nucleus breaks into multiple different elements, what happens? They do not just rest beside the nucleus. They are gaining the excess unstable energy, and then they are propelling themselves forward. Okay, they are propelling themselves forward with this unstable energy. Okay, now this consequence is, so basically, if there is nothing out around them, then it's of no concern. There is no concern regarding it. If it's an isolated atom that is nowhere near any other atom, then it's an isolated event. Nobody cares. But if there are radioactive elements around me, then what happens? Imagine this: when the first container falls to the ground, as soon as it breaks into two, that like the lid and this, another container starts to break, starts to fall, and another container starts to fall. So basically it's like multiple containers are simultaneously falling onto the ground because one container fell to the ground. Similarly, when one atom breaks, then it influences the surrounding atoms around it, creating a chain. It is creating a chain like this. Okay, let's look at it in more detail. Now, a fixed quantity of energy from the decay is available to the two decay products. Okay, that is the unstable energy that basically was there in the parent atom has split itself, and it is imparted into the multiple elements. So basically, when you split something, you will get at least two pieces.
Yeah.
Okay, when one element breaks, one thing is for sure is that you will have multiple pieces. Okay,
Yeah.
otherwise break does not mean any sense, right?
Yeah.
Okay, so the energy that was present in the parent atom has now been delivered to these daughter cells. Okay, these daughter elements. Okay, thus what happens? They, because with this energy they are going to propel forward. Okay, the energy must be conserved as it is shared, but momentum must also be conserved. When the parent nucleus is stationary before the decay, the momentum is how much? Zero. Do you remember me teaching you the bomb concept? Initially, the bomb was stable before the blast, but after that, therefore, the initial momentum is zero. But after the blast, the bomb splits into two, having two different masses. Then both the particles will move in the opposite direction to cancel their momentum out. I think we have learned this in kinetics. Exactly. Yeah, the recoil back. Okay. Now, the total momentum after the decay must also be zero. In an obvious notation, mdvd is equal to minus m alpha v alpha. That is, d is what? This thing. Okay. this thing, okay, and alpha. Now, with a fixed amount of energy at disposal of the system, the speed of the alpha particle away from the site of the decay and the recoil speed of the daughter nucleus are completely determined. Although the momenta are shared evenly, energy is not. The alpha particle is much less. The alpha mass is much less than the nuclear mass of the daughter, and so the initial alpha energy is likely to be much more than the initial energy of the daughter nucleus. So what is it trying to say? Basically, when you shoot a gun, does the bullet have more speed or the gun has more speed? The bullet will have more speed, right? Obviously the bullet will have more speed. Why? Because the mass of the bullet is less. So when you're imparting energy, the alpha particle being much more smaller, which will gain much more kinetic energy. It will gain more energy than before. Okay, so the emitted alpha speeds are initially the same. The emitted alpha speeds are initially the same, and the alpha particle loses a roughly fixed amount of energy per collision with each air atom as they travel. This means that the alphas with the same energy from a particular nuclear decay travel about some distance as each other, as shown in the alpha track. That is what the radiation radius means. Okay, every time a bomb is dropped, okay, the center of the bomb, the place of the center of impact, releases particles, these radioactive particles, all around in the form of a sphere. Okay, but these alpha, beta, and gamma particles that are being released from this bomb blast can only travel a certain distance before their impact is like negligible. The people inside the radius will obviously have the impact, but the people that are outside this impact radius won't have much effect. Am I right? They won't have
Yeah.
much effect. Now, patterns and trends. One of the reasons why a large particle with four nucleons is emitted rather than a smaller proton is the energy bound up in the alpha particle. Okay, listen to this. One of the reasons why a large particle with four nucleons is emitted rather than a smaller proton, that's why basically they're trying to ask you, why doesn't the radioactive element just send out a nucleon, they just send out a proton? Why four protons together? Like why two protons and two neutrons together, creating an alpha particle? Is it of some concern that only four can come out in one go? No, that's not the case. The reason is that this is why is it so? With four nucleons is emitted rather than the smaller proton is the energy build up in the alpha particle. Okay, this is large. Alpha particles are exceptionally stable. Once outside the nucleus, the alpha particle is a helium 4 nucleus and can exist as a stable entity. It is energetically preferable to allow the alpha particle rather than the two protons and two neutrons to leave the nucleus. It's like this. When we are small, okay, we are stupid, we are more energetic, right? When we are small, we are more stupid. So do the parents allow us to leave alone? No, right?
Yeah.
But when we are big, when we are like 20, 25, do our parents say, oh Akshay, don't go outside, it's outside is scary? No, right? They basically kick you out of the house and say go outside and basically explore. Okay, so just think about this. When you have a nucleon, 1 second. So when it is much more energy efficient, it is a much more since the alpha particles are big enough, they can take out more unstable energy from the nucleus as compared to four individual nucleons.
Yeah.
Okay, they have
Yeah.
the ability to carry more unstable energy than four individual nucleons put together. Okay, now an alpha particle will have an absolute potential energy of around 6 mega electron volts, and this is substantially less than the potential energy barrier that prevents particles leaving the nucleus. Imagine the barrier as a fence over which the particle must jump to escape. Under a classical view, when there is little to no energy, then the particles cannot reach the top of the fence. The alpha particle leaves the nucleus through a quantum mechanical tunnel. The probability wave that describes the alpha particles gives a small but finite probability that the particle can exist outside the nucleus. Okay, I think it's called quantum tunnel. I don't know. Okay, I'm not that much of a big expert in like quantum physics. Okay, I know a little bit, but not to this much extent. Quantum tunneling and all. Okay, so
Yes.
basically, the reason why an alpha particle is preferred rather than protons is because they have the ability to carry more energy, and they can exist outside the nucleus in a stable manner. Okay, like basically if they go outside the nucleus, they won't just simply disintegrate and come inside. Okay, they can exist in a stable fashion, in a stable manner outside the nucleus. That is why they are exhibited as four in a pair, not individual nucleons. So two protons and two neutrons will come together and then exit the nucleus as one single alpha particle. Okay, understood? So, so that brings us to the conclusion of the first video of this chapter. Okay, I hope you really enjoyed my explanations on this chapter. Okay, I will try to create as many realistic examples as possible to these new ideas and new topics that you're going to learn. Okay, so that you can imagine what is happening in physics at this point. Okay, so if you like my videos, please do like, share, and subscribe. And I'll see you in the next class. Thank you so much and have a nice day.